Assalamualaikum, my name is Rehana binti Abdullah, number matrix TE210089. I would like to introduce you our group members, Hana Syahira binti Rosli, Nur Syahira binti Muhammad Saleh dan Siti Asia binti Ismail. So we are from group 5, section 2, and our lecturer is Prof. Madia Dr. Rosli bin Umar. So, introduction. Control system engineering requires knowledge of at least two basic components. That is the plant, which describe the mathematically model of your system, and the output is the goal you are trying to reach. Control system has become commonplace in the automotive industry. In the cruise control system, control system has to manage all of the vehicle readings in order to maintain velocity. Most of the control system are implanted using PID control because its simple structure, ease of implementation, and active research in turning the PID for a long time. So we learn to search PID control tuning instantly using MATLAB. We have learned how to automatically tune PID control block using PID tuner, and then open the engine speed control model with PID controller. So I will show you open loop system using MATLAB. So first we open the MATLAB, and and then search simulink. First we find the source, and we use step, and then bring it up. And the second thing that we want is continuous, and then we choose a transfer function, and the last is scope for the output, and then we arrange. Okay, this is the scope for the input, this transfer function. Then I will change it to the 5. Okay, and then this s, the same 1 equal to s, and then 12 s power of 2, and then 1 equal to s power of 3, 12 s power of 2, and then 21 s power of 1, and 10. And apply, and okay. So for here we repeat that. Then you can see the decimal, the number in this transfer function, and then you connect the block. Okay, and then we start the time to the 10 seconds, and that's all. So we can run. Wait. Okay, and successful. So and the plot, the graph will appear after we push the scope. So that's all. Thank you.
Hi, Assalamualaikum. My name is Hana Syahira binti Rosli, number matrix TE210107. I'm gonna make the closed loop system setup and P controller. The closed loop system is which there is feedback path present. First, you need to open the MATLAB and then click the simulink button, and then we gonna choose the blend design, and after that it's gonna show like this. After that, we need to click the library browser to find the product, which is step, sum, function, and the PID controller. After that, we just connect each other and you get the closed loop design. When you click the PID product, you can see here this is broad parameter for a PID controller, and you can see the proportional value is 1. So this is the value for the closed loop system. After that, when we double click at this step response, and you can see the value is 1010, and then we need to change the sum to plus minus, and for transfer function you need to change to our value, which is 5. The denominator is the 1, 12, 21, and 10. After that, we need to change the stop time to 15. After that, you're gonna run as normal, and then you can see the graph. This is the graph from the output scope for the closed loop system. Next, we're gonna continue to make the P controller. The function of P is proportional term, which is present element. To speed up the closed loop response, the proportional term minimized but does not eliminate the steady state error or offset. First, we need to change the PID controller to P controller, and then you can see here the proportional value is 1, and then you need to click the button turn to automatically turn in. After that, you can see the graph come out. Here you can see this is the graph step block P controller after auto tune, and then you need to click the update block to remove the block response, and then click the show parameter, and then you can see here this is controller P parameter. After that, you need to click again to PID controller, and then you can see the proportional value is changed, and then you need to run, and then make sure the stop time is 15. Here you can see the graph of the output at scope P controller after the auto tune, and then you're gonna click the command up here to find the P finder, cross measurement, behavior measurement, and from this you can see the value for the rise time, setting time, overshoot, and peak tension response. That's all from me. Thank you.
My name is Siti binti Ismail. My matric number is CDE210102. Next, I will be performing a simulation for PI controller and PID controller. So let's take a look at PI controller. So this is the block diagram of, this is the Simulink model of the PI controller, which is the same of like the P controller, since this is a closed loop system. So what makes it different from the P controller is that in this PID controller, we will be using a controller of PI. Instead of P and PID controller, we will be using the PI controller. But for the value of the proportional and integral gain, the P and I gain, we will just let the value as it is, since we're going to use the automated tuning of the PID tuner. So basically, what is the why we use the automatically tuner? Because we want to achieve a desired performance and meet design requirements. And this auto tune tune a PI controller in real time against a physical line. So we're gonna tune this PI controller. Okay, so you can see it is currently simulating. Okay, so we can see here the step like of the reference tracking of the PI controller after we auto tune it. So this is the full line here is a system response with a tune controller, and the dotted line is the system response with initial PI gains in the model. So we update the block. So we can see after we update the block, there is only a tune response of the system, and then we're gonna click show parameters here to see a value of parameter P and I gain. So we can see from this table, the P value after we tune it is 4.499, and I value is 1.4361. For the D and N value, there is no value since this is a PI controller. So we're gonna close this tab and go back to the system. So we're gonna set take a look at this value of proportional and integral P and I gain. This is the value after we auto tune this Simulink model. So tekan OK, and we're gonna run this Simulink model to see how the system responds to the PI controller. Okay, so this is the graph of PI controller that we can see from the scope. So to measurement and cursor measurement. So from this graph and this by level measurement, we can see that the overshoot of this system is 4.737%. And the rise time here is 1.169 second. So we can see for a detail, we can use the PID finder. Okay. Here is the PID traction response of the system, and somewhere between here is we can see the settling time of the PI controller. So what makes PI controller different from the P controller is with the added value of I integral gain, we can see that the overshoot and settling time is increased, but we can see the rise time is decreased compared to the P controller, and then we can see there is no steady state error. The steady state error have been eliminated. So I think that's all for PI controller. Okay, next let's move to the simulation of the PID controller. So the Simulink model is still the same as before, and the difference here is at the PID controller, we gonna at this controller we gonna change it to PID, and here we can see the proportional, integral, and derivative value is 1, 1, and 0, and the filter coefficient n is 100. We are not going to insert the value of P, I, and D gain manually. The process is still the same as the previous PI controller and P controller. So we're gonna apply and tune this controller. Okay, from this step plot graph, we can see the dotted line is the system response with initial PI gains in the model, and the full line is the system response with tune controller. So from this, we can see that the controller parameter here, the P value is 4.621, the I value is the 2.949, the D value is 1.773. So after updating the block, we can see the only left response is the system response with the tune controller value, and click the show parameters to see the value of the settling time, response, steady state error, overshoot, rise time, and etc. So we can take a look at the performance and robustness of the system response. The rise time after the tune with left with 0.465 seconds, settling time is 1.84 seconds, overshoot is 7.47%, and the closed loop stability is stable. So okay, after we tune the PID controller, we can see the value of proportional P, integral, and derivative is automatically insert with the value that we get from the tuning process. So click OK, and we can run the simulation to see how the system responds to the given value of P, I, and D. Okay, click at the scope. Now we can see the graph of the PID controller. To see more detailed information, click the tools and measurement, bi-level measurement, and cursor measurement. So from this bi-level measurement, we can see the value of overshoot is 5.851%. The rise time is 1.288 seconds. So we can see the rise time here is very fast compared to the P controller and the PI controller, and we can see there is minimum overshoot and settling time compared to the previous controller, and also there is no steady state error of the PID controller. So I think that's all for the simulation. Thank you.
So the conclusion is, in open loop control system, called a non-feedback control system, there is action from the control system independent of the process output, which is the process variable that is being controlled. So we have three types of control. That is closed loop, controller, PID controller, and PID controller. P is for proportional, I stand for integral, and D for derivative. So P controller is mostly used in the first order process with single energy storage. P controller is to decrease the steady state error of the system. PI controller is a feedback control loop that calculates an error signal by taking the difference between the output and system. PID controller is used in industry control application to regulate temperature, flow pressure, speed, and other process variable. PID are used to control loop feedback mechanism to control process variable and are the most accurate and stable controller. That's all from me and our group. Thank you.